Hi everyone, welcome to lecture number 13 for Physics 151. This is a continuation of Newton's laws, specifically Newton's second law. There are a number of applications for it, and today we will cover some examples involving 1D and 2D force problems. So this lecture will have very little theory. In fact, it's just going to have a little review of the theory from the previous lecture, and it'll be mostly working through some examples. I've divided the 1D and the 2D problems into tutorial 13A and 13B just to make the files a little smaller, but it's all the same sort of thing. And this is related to online homework 13 to 15, which is a single assignment, which only has about 9 or 10 problems. The first half of those problems, about the first 5, are a few examples of 1 and 2D force problems. So first, let's just start with a review of Newton's second law. You'll remember that of Newton's 3 laws, the second law is the one that is the equation. It's the one that says that acceleration is the result of net force acting on an object of mass m. So that's where acceleration of any object comes from. It comes from when there is a net force present, external, some net non-zero sum of external forces acting on a mass that we define. Now, we can use the Newton's second law as a full vector equation written right here, where A is a full vector in either x and y components or magnitude and direction. And each of the force vectors is the same. And then we do a vector sum here of all the forces. Or what you're going to find is that for many problems, it's more convenient for us to separately write Newton's laws for x components of all the vectors, y components of all the vectors, and if we wished, we could write another one for the z components. However, we're not going to have any of those three-dimensional problems in this class, so I've just left it off. It turns out in a lot of the problems that we're going to be doing today, this will be the way that we'll approach it. We will look at just the x components or just the y components of all the force vectors and use that to get just the x or y component of acceleration, or vice versa. Sometimes we'll know the acceleration in a particular dimension, and we will use that to solve for an unknown force. Now, our textbook in section 5.1 talks about equilibrium. So it's worth at this point just briefly mentioning what is meant by dynamic equilibrium. Well, a system or a mass m, or which could be either a single object or a system of objects, however we define it, is in dynamic equilibrium when the net forces acting on it all sum to zero. When that is true, then we say that the system is in dynamic referring to the forces, equilibrium referring to all the forces balancing. So when you add those force vectors, they add tip to tail and they'll sum to zero. What that means is that the object or system, pardon me, whatever mass m refers to, mass m will end up having zero acceleration. We could write this independently in different components, x or y or z components. What that means is when you would have zero acceleration, at least in the x direction or in the y direction. This is what happens when an object is sliding along a surface and that surface is parallel to either the x component or the y component. Then the object doesn't move in the perpendicular direction. So that would be true. We'd have zero motion in the perpendicular direction, which means that the forces in the direction perpendicular to the surface must sum to zero. When you have zero acceleration, of course, that means that your velocity must be constant. It is possible for that constant value to be a zero value, in which case we have the special case of rest, and that has its own name. We say that that particular special case of when the mass m is continuously sitting at rest is called static equilibrium. So it's just a special case of dynamic equilibrium. And as you can see, we don't get anything new out of or there's nothing new that we can plug into Newton's second law in this case. Static equilibrium, dynamic equilibrium, they both tell us that the acceleration is zero, or and therefore the sum of the forces is zero. The only additional piece of information is when something is in static equilibrium, that means there's no motion at all. And that means that the speed at all times will also be zero. And there's also zero displacement as well. That's what you want for things like a building or a bridge where it's not supposed to move at all. Right. This is also a review from lecture 12, and this is just a reminder to us of sort of the steps that I'm going to follow in all of the example solutions that I show you. First, and this is something that I forgot to add in lecture 12, so I've just called this step 0, which is, so this is a little nod to all of you computer science majors out there. We'll start by our enumeration at 0. So first, define what you want the mass m to be in Newton's second law. In the F equals ma, what do we want m to be? Because what we're going to put into Newton's second law then is all of the forces that are acting external to m. In other words, acting on m from the outside. We are going to omit all the forces that act inside of m between different parts of mass m. So if mass m is a block of wood or a book, we omit all of the internal forces between the individual molecules and atoms, for example. And we only care about forces that are acting on the book from the outside. Okay, so sometimes strategically, we will choose our mass of interest to encompass 2 or 3 or more objects and be a system of objects, in which case we will, in our free body diagram that's coming up in the next part, we will omit all of the internal forces and we will only inventory the external forces. So that leads us to step 1, which is create a free body diagram of this mass m, right, whatever it might be. On this free body diagram, show all external force vectors, okay, that are acting on m from the outside, right? Omit anything that is acting internally between parts of m. And the reason is because all those are Newton's third law pairs, and they'll all sum away to 0, so we can omit them all. All right. Now, what we've just done by doing the free body diagram is we've just created a visual inventory of all of those external force vectors that are going to go into the net force or total force of Newton's second law. Now, in order to do that vector sum, there's sort of a mathematical step that we need to do, which is, all right, if we're going to deal with the vectors and components, for example, we have to define what the directions of the coordinate axes are going to be in our diagram. Now, it turns out we can choose our axis directions strategically to make our math and our analysis simpler. So these are going to be common things that we're going to do. If there is, if the object is moving, for example, then we will often choose one of these axes to be along the direction of motion. So if it's an elevator moving up or down, or a block sliding to the right or to the left, we'll choose the Y or X direction to lie along that motion. If we have a ramp or an incline, which I will skip those problems this semester, then we would usually rotate our axes to choose our axes to be parallel to that ramp or incline and perpendicular to that ramp or incline. And again, it may sound like that's making things more complicated, but it ends up making our math simpler in the long run. If we have a spring in the problem, we're going to choose one of these, usually the X direction, to be along the spring, because springs only pull or push along each other. You could do the same thing with tensions along ropes. Well, potentially. But springs, yes, we usually will do that. That'll be our custom. Now, at this point, we have inventoried all of our forces. We've chosen our coordinate axes. Stick to your choice for the entire problem. If we know all of our force vectors, and if all we're trying to do is, say, solve for the acceleration, then we can just go straight to the full vector equation of Newton's second law. And we don't need to, so I've omitted step 3 here. We don't need to bother breaking down the forces all into components unless we choose to do a component method vector addition for this sum right here. Otherwise, if we want to just use triangle method or some other just, graphical method for the vector addition, then great. We can go ahead and do that. And then we multiply by 1 over m and we get our acceleration. Or there might be a few cases where you have dynamic equilibrium, in which case you know that the sum of these forces will equal 0, and then one of the forces might be unknown. So then you can say, oh, unknown force is equal to the sum of all the sum of all the other forces. And then just, again, use the full vector equation and you're done. However, there will often be the case where there is one component of one force that is the unknown, or perhaps one force that is the unknown. And in order to really isolate that and solve for it, we will usually have to choose to take all the forces and decompose them into their x, y, or x, y, and z components. Here, I've only just shown two-dimensional. Once we've done that, Then we will apply Newton's second law separately for all the x components of everything and separately for all the y components of everything. And if we wanted to, we could have a z component equation as well. What this will do is this will allow us to have perhaps systems of simultaneous equations, right? We might have two unknowns like a sub x, and tension might be one of these forces in here. And then tension might show up again over there. And then we'll have two equations with two unknowns. Oftentimes we will know one of these accelerations to be zero. And then that allows us to solve for some force components. And then that can either answer some questions or we can plug it into the other equation and solve for remaining force components. So you'll see that with some of these problems, you'll to be able to tell at a glance that, oh, we probably want to do this component breakdown. If in doubt between using the first method or the second method, go with the second method. The component method is usually it generally works for everything and works for all situations, right? The first method can be faster, just using full vectors can be a little faster for certain special cases. All right, that's it. So that's our review of theory, the review of Newton's second law, and some of the typical tips for steps that we use when solving these dynamics problems. So now let's do some examples. I'm going to show 4 examples out of the 6 problems from tutorial 13A. And then I'm going to also show 2 of the 4 problems from tutorial 13B. So that'll leave a few more problems unshown here, although the solutions are already uploaded, and you can try those for additional practice. Okay. All right, I'm going to switch my input now, and I'll probably pause the video at some point in the middle of these problems just to keep the file sizes a little bit smaller. All right. So here we have tutorial 13A. And again, I'm going to show problems 1, 2, 4, and 6 as sort of example solutions. I might skip 1 or 2 parts of these problems, but otherwise I'll try and show most of them. So this is just a summary of what was on the previous slide, that list of sort of solution tips for solving dynamics problems. Okay. Just a moment, let me reorient here. Okay, great. Okay, let's take a look at problem number 1. Suppose that we have a bucket suspended from a vertical rope, okay? And at various times the bucket is raised or lowered, but there's no horizontal motion at all. All right, well, I think that, and then we're asked different questions about either the tension in the rope, or I'm sorry, the acceleration, the vertical acceleration of the bucket, or the tension in the rope, okay? Given one, what's the other? I think that the best approach here would be for us to define our mass of interest to be just the bucket. So I'm going to say, okay, suppose that this is our bucket right here, mass M, and I'm going to create a free body diagram of this bucket that shows all of the forces that are acting on it. So if I think about, given the description of the problem and given what else I know about physics, I think that there is a weight acting on the bucket, and I know that the weight always points downward toward the center of the earth. Now you're welcome to call that W. I'm going to choose to call my forces capital F with a subscript, but you're welcome to call that lowercase w, just like our book and many books do. And then, is there a normal force? No, there is no surface that the bucket is in contact with. Is there a spring acting on it? No, there is not. So there is a person pushing, no, well, not directly. We don't know what the rope is attached to, but what we know is that there is a rope attached to it and the bucket is suspended or hanging downward from the rope. So that means that this rope is going to create an upward tension. So you can call that capital T like our textbook does. I'm going to call it capital F sub T. Okay. All right. Before we can do any additional math, we have to define our component directions. So I need to choose what direction is going to be the positive y direction and what's going to be the positive x direction. And then any components that I write down of these force vectors and accelerations will have the right plus or minus sign. So I think this bucket's going to be moving up and down. It's a natural choice for us to choose one of our axes in that direction. You could choose a positive y direction to be downward if you wanted to, but for me, upward is just a more intuitive choice. So I'm going to stick to that. This x direction we don't even need to define because we're not going to need it. There's going to be zero horizontal motion. So in some problems, like an object sliding on a horizontal surface, there may be zero motion in the vertical direction, and while there are forces in the vertical direction. But in this particular case, we don't even need to define this because there's no horizontal component of any of the forces and there's no horizontal motion either. So we're not even going to use the x direction. All right. Now, at this point, I'm going to go ahead and use the component step. So I'm going to say, all right, now that I have my free body diagram where I've inventoried all of the external forces acting on our bucket, which is the mass of interest, now I'm going to express each of these external forces in components, all right? And what this will do is we'll find that the x direction is pretty boring, okay? But at least it'll help us to know everything we know about those forces, and it'll put the correct plus or minus signs. So decompose forces into components. And I can say, okay, what do I know the components of the tension force are? Now, we could say, oh, look, the tension force is at a trig angle of 90 degrees, so that means it needs to be magnitude Ft times cosine 90, comma, magnitude of Ft times sine of 90. And if we did that, cosine of 90 is 0. I'm sorry, cosine of 90, yes, is 0. So we'd have 0 in the x component. And then the sine of 90 is 1. So we would just have Ft times 1 times plus 1. And that's it. So I'm just going to put a little plus sign here to remind us that this is the magnitude. And this is in the positive y direction, not the negative y direction. And magnitudes are always positive quantities. So that is a positive quantity right there. This is not a component anymore. Well, this whole thing is a component, but Ft by itself is the magnitude of Ft, which is a positive value. Okay, I hope that's legible. All right, let's do the same thing for the weight. So notice I just did this I could have just done this by inspection, and that's what you're going to see me do for the future ones when the components of the force vector lie exactly along one of the coordinate axes, and we can tell just by looking at the vector. Oh, look, this tension has no x component, so by inspection, 0 for the x component. And the same thing for the weight. The weight has no x component, so the x component will be 0 just by inspection like that. Y component of the weight will be the entire magnitude of the weight in the negative y direction. So again, by inspection. I mean, we could say, oh, it's equal to magnitude of weight times sine of 270, but sine of 270 degrees is just negative 1. So negative y direction, and then the magnitude of the weight. Well, what's the magnitude of the weight? Right? In other words, the magnitude of the weight. We know what that is. This is one of the few things we know. We don't have an equation that tells us the magnitude of tension in all cases. We have to solve that specifically for every problem. The same is true for normal force. There's no one size fits all equation for normal force, but for weight, there is a one size fits all equation. Regardless of how this bucket is moving, we know that the weight is always going to have a magnitude equal to m times g. So whether this bucket is moving up or down or accelerating or at a constant velocity, it doesn't matter. The weight never changes. It's always going to have a magnitude of m times g, and it's always going to point toward the center of the Earth, which in this case is our negative y direction. So that is fixed, regardless of the motion of the bucket. Okay. Tension, on the other hand, is not fixed. It will vary depending on the acceleration of the bucket, as we will see. All right, that's it. We're done with breaking down our forces into their components. We've inventoried all of our forces. So we're ready to go on to the last step, which is to apply Newton's second law. Okay. Now, if I were to apply Newton's second law to the horizontal direction, it would be a very boring sort of story, right? We would say the sum of all the x components with 0 plus 0 is equal to mass times acceleration in the x direction, which is also 0 because there's no x motion. There's no horizontal motion. So we're going to just skip that and go directly to the vertical direction. Okay. So let's add up all of the y components. So that's what this notation means. This just means sum up all of the y components of all forces, right? And that's going to equal the mass times the y component of the acceleration. Remember, so the acceleration is a vector, and it has a y component and an x component. The x component in this case is 0. All right, so the y components of all these force vectors, I'm going to be a little explicit this time, but in the future, I'm not going to be so explicit. It's the y component of the tension force, it plus the y component of the weight. And we can see by looking up here at our list of all of the forces, the y component of the tension force is just +1 times the magnitude of the tension. And the y component of the weight is -1 times m times g. And that's the y component acceleration of the bucket. Now, at this point, some of these things are known, right? Mass of the bucket is known, g is a constant, but some of these things are unknown, right? For some of these problems, we're given the tension magnitude and we're asked to find the acceleration. And for other problems, we're given the acceleration and asked to find the tension. So it looks like this will be one-stop shopping that we can do where we use this equation over and over again, and we can keep using it for any acceleration and any tension values as long as nothing changes up here with our free body diagram. Okay, so, right, if we were to introduce a new force, like, I don't know, air drag or friction or another tension of another rope pulling on the bucket, maybe upward, like tension 2 upward or tension 2 downward, then the free body diagram has changed. We would add another force to our list of forces, and Newton's second law would have a new force on the left side. So all of a sudden the equation would be different, okay? So if we change anything about the free body diagram, anything about the free body diagram, and therefore something about these forces would be changed. We either add one or delete one or change the direction of one or something like that. Then we have to redo the left-hand side of Newton's second law here, and then this equation would change. But it looks like throughout this entire long problem here, in all of these parts, there's just one tension pulling upward on the bucket, one weight going downward, and that's it, and no other forces. So I think we can use this equation with confidence throughout the entire problem. All right, great. So let's do it. So let's take a look here at part A, although I'm going to write the work for it down below the bottom. At a particular moment, the tension in the rope is known to be 63 newtons. What's the bucket's acceleration? Okay, and by that, I guess we can mean magnitude and direction. All right, so let's do that for part A. So for part A, we're given the magnitude of the tension is 63 newtons, and then we can solve for the acceleration. Now, there are other things. You can write this algebraically in different ways. You can collect terms, collect the masses, etc. I'm just going to go ahead and leave it this way, but there are multiple correct ways to do this. So the tension is 63 newtons. Notice this is the weight, right? So I'll go ahead and plug in what we know. And here's our unknown, the acceleration. Granted, this is only the y component of the acceleration, but still, we've already been told the x component is 0, right? There's no horizontal motion at all. So this is 63 newtons minus 98 newtons. Uh-oh, looks like my acceleration is going to turn out to be negative. Is that okay? Yes, because this is just the y component. That's why. So it's okay for it to be negative. Well, I'm sorry, it's only 2 sig figs. So it's okay for the y component to be negative. What does that mean if the y component is negative? So that means the acceleration vector has a magnitude of, oops, that I just meant that to be an equal sign. Means the acceleration vector as a whole has a magnitude of 3.5 meters per second squared, and the direction is downward. Okay, so that's what that tells me, right? The y component is negative, so therefore the direction of the whole vector is downward, because we know there's no x component. Right? Or if we just ask for the y component, fine. But if we're asked for the magnitude is always positive. So the magnitude is 3.5 meters per second squared. Y component is negative, so the direction is downward. No x component. All right. So the answer is D. Let's do another one. Part B. At some other time, the same bucket with the same rope attached to it to its top undergoes an upward acceleration of upward acceleration, pardon me, of 1.0 meters per second squared. So the direction of the acceleration is upward. Okay, so positive y direction. What's the magnitude of the tension in the rope at this time? Okay, so let's use the same equation again. I'm going to put a little wall here, so I don't confuse the math too much. All right, so let's use our same equation over here. Right, nothing's changed about the free body diagram, so we can use it again. Tension minus weight is equal to mass times y component of acceleration. In this case, the tension's the unknown. I've already calculated the weight down below. It was 98 newtons, so I'm just going to recycle that information here. It's equal to 10 kilograms times 1 meters per second in the upward direction, so it's positive y component. Okay. So it looks like the tension in the rope is 108 newtons. Okay. And you could say I might have gained a significant figure here just due to carryover, due to addition. Good. So once again, the component here, I'm sorry, this is the magnitude of the tension force. If I want to know what the components of the tension force are, or the direction, pardon me, the direction, all right, we just know from the situation of the problem, the tension always acts in the upward direction. Okay, so the magnitude is 108 newtons in this case, and the tension is upward. So notice in this earlier case of part A, the tension was less than the weight, right? Which resulted in a downward acceleration of the bucket. In part B, the tension is greater than the weight, and it results in an upward acceleration of the bucket. Does that make sense? Yes, that's exactly what we would expect from Newton's second law. Right? If we were to sum these two y components of the two forces, if the sum of those y components is in the downward direction, then that should result in a downward acceleration. If the sum of the y components is in the upward direction, which would happen whenever the tension is greater than the weight, then we would expect the y component to be an upward acceleration. Okay, so when the tension is weaker than the weight, the bucket is accelerating downward. The result is downward acceleration. If the tension is greater than the weight, the result is upward acceleration. What if the tension is exactly equal to the weight? Well, then we have dynamic equilibrium, right? And in that case, we would have the tension equal to mg, and the left-hand side of this equation here would just sum to 0. Okay? And in that case, the acceleration would be 0. And that's what we have here in this last case. We have a constant speed, right, of downward 0.33 meters per second, right? So you could say the velocity has a y component of negative 0.33. That would be another way to write that, right? But that means this is constant over time, meaning unchanging over time. So that means that the acceleration is 0, right? So what that means is the tension is just equal to the weight, which is equal to 98 newtons. This would be true whether we had a constant upward speed or whether we had a constant 0 speed or a constant downward speed. Any of those situations describes a dynamic equilibrium case where the acceleration is 0. Now, the bucket doesn't have to be at rest. It just has to be not accelerating. It could be at rest. In all of those cases, rest, upward constant speed, and downward constant speed, the tension of the rope is exactly equal to the weight. All right. Let's take a look now at problem 2. Now, problem 2, I wanted an example where we're doing some horizontal force summing. And it just so happens this is sort of a very basic two-dimensional problem. But it's a two-dimensional problem where all of the forces are aligned only along the x component or y component directions. So it's kind of a trivial 2D case compared to the ones that we're going to do near the end of this lecture, which are more complex and the forces have diagonal components. Okay, so suppose that a very large concert grand piano is on a frictionless dolly. The total mass is given, and there are 2 people pushing exactly to the right and 1 person pushing exactly to the left. So there are 3 horizontal forces acting on this object. So I'm going to go ahead and assume that the piano is our object of interest. There's only one sort of mass that we're talking about here. Okay, so this is the piano. It's on little wheels. Notice my minimalist drawing. That's all you need for a free body diagram. Okay, and we have 2 forces pushing to the right. And these forces, I'm just going to draw them at some random length here, but they're going to vary their magnitudes throughout this problem. Okay, so for example, sometimes we're given how strong force A. Then notice how the names of the people are A, B, and C, right? So that'll make our subscripts easy. So notice how sometimes we're given force A and C and asked for force B. Sometimes we're given force A and B and C and asked for the acceleration. Okay, it looks like at no point does anyone push in anything. At no point does anyone change the direction of their forces. So no one pushes at a diagonal. No one switches sides and pushes in the other direction. They just maintain their original direction. So we have forces A and B to the right, and we have force C to the left. Now, if we want to really be complete with our free body diagram, we know that there's, and now I don't have room on the page to draw these forces their proper length, right? If these are, tens to hundreds of newtons, then it turns out that the weight of this 500 kilogram piano is like 5,000 newtons. So this vector would go way down the page if we were to sort of draw it to scale with everything else. I'm just going to draw it as a long vector, and we'll just remember that it's actually huge. Okay, so you can call that the weight if you want. This is a side view, right? So the weight goes downward on our diagram. And then there's a normal force from the floor, which I'm just going to draw acting on the center of the piano, even though it's really coming from the wheels. I'm going to sum it all up and just call it a single normal force instead of separating it out. Okay, and that's it. Those are the 5 forces that I could think of that are acting externally on this piano. If I'm going to use any components, I'm going to need to define my axes. Let's call positive y upward, negative y toward the center of the earth, positive x to the right, negative x to the left. Okay. Again, we could reverse those choices if we wanted to, but we're used to these directions, so that's fine. All right. This will keep our math simple, because notice we've chosen components that lie exactly along these force vectors. If we wanted to, we could have chosen our axes at some weird angle like this, and then we'd have to decompose all these with weird trig angles along the x and the y components, and that would actually be a lot of extra work for no real gain. Right, now we can decompose these into their components. I'm going to do this a little faster this time. I can just do this all by inspection. I can write out the three people's forces. I can see that they're all exactly along the positive x or negative x direction. So I can say the entire component lies in the positive or negative, I'm sorry, entire magnitude lies in the positive or negative x direction. So this is a magnitude, magnitude, magnitude. These are positive quantities. Okay, notice they have no vector hat on top. And then the y components of all these vectors are just all 0. Okay. Normal force, I can see lies exactly along the positive y direction. So I can give it 0x component, but I don't know how strong it is, right? And then weight lies exactly along the negative x direction, and we do know exactly how strong it is, regardless of the piano's motion. I said negative, I'm sorry, did I say negative? Negative y direction. We do know exactly how strong it is, regardless of the piano's motion. All right, that's it. Now we're ready to move on to Newton's second law. So now we can apply Newton's second law. We can apply Newton's second law to each direction. Let's see if something interesting happens. Right, in the horizontal direction, we have the sum of the x components of all of the forces. I'll zoom in just a little bit here. Okay, so it's getting too small. So on the left-hand side here, we want the x components of all 5 of these forces. We can see these are 0 over here, and those we're just going to add up. So this becomes the magnitude of FA plus the magnitude of FB minus the magnitude of FC, and that will be equal to the x component of acceleration of the piano times its mass. So that's our horizontal equation. In this case, I don't think we're going to have any crossover between the two equations, but in many cases, if you have a diagonal force, for example, then you'll have a crossover. You'll have something like maybe tension or the force from a person appearing in both of these, the horizontal and the vertical equations. In this case, I'm going to add up the y components. These 3 are all 0, and then on the right-hand side, I have magnitude of normal force minus magnitude of weight is equal to, now I'm going to go ahead and use additional knowledge that I have, which is that this piano never moves in the y direction, right? Even if we were to, even though there are forces acting in the y direction, right? There's weight and there's normal force. We know that the piano only rolls to the right and to the left along the stage. So that means the displacement, velocity, and acceleration in the y direction will all be 0 at all times. Okay? So I'm going to use that knowledge, right? So there's no motion in the y direction to be able to say, therefore, the normal force is just equal to m times g. So this is one of the cases where the normal force is equal in magnitude to the weight. Okay, and the normal force and the weight simply cancel each other out. That's not always true in every case, right? That's why we can't just write down the normal force is just always equal to mg in magnitude every time. That's not true in general. Okay, so in theory, we can now answer any of these questions just using these two equations. Okay, and in fact, if I jump down here to part D, we can say well, you know what? Let's take them in order. Okay, so at a particular moment, the piano is moving to the right at a constant speed. Okay, and given our choice of axes, that'd be a velocity with an x component of positive 18 centimeters per second. Given the magnitudes of the force from person A and person C, what is the magnitude of the force from person B for that to happen? All right, well, we're talking about horizontal motion here, so let's use our horizontal result from Newton's second law. Okay, so I'll just reproduce that up here. So what do I know? I'm given FA, I'm given FC, I'm asked to solve for FB, okay, so this is my unknown, and I know that this is equal to 0. So we can go ahead and plug in 250 newtons for the magnitude of FA, 435 newtons for the magnitude of C, and that lets me solve for FB. In other words, this is a case of dynamic equilibrium. Right? The three people, their forces are exactly balancing each other out. So even though the piano is in motion, it remains in motion at a constant speed. The forces sum to zero because there is no acceleration. Okay. Now at a different time, suppose the piano is accelerating, and we're given all three of the people's forces. And it looks like we want horizontal acceleration again. So I think we want to use the exact same equation again. Right? It might be a little tight for me to squeeze it all in here. All right, let me try and squeeze it under the problem. So we're going to use the exact same equation. I'll start using the same equation again. Now build a wall here. Okay. Now all three of these are given 150 newtons plus 150 newtons minus 260 newtons. And that's equal to mass of the piano times horizontal acceleration. Okay, if I add up these all of these forces on the left side, looks like they all add up to just 40 newtons. Looks like I just lost a significant figure due to subtraction. Okay, that happens. I'm just repeating the line above, and then we get that the x component of the acceleration, therefore, is positive 0.07777. So it's rounded to 6.078 meters per second squared. So that's the x component of the acceleration. The acceleration of the piano in y direction is zero at all times because it stays on the surface of the stage. So what is the magnitude direction of acceleration? Well, we can see the magnitude therefore is just the x component, 0.078, and the direction is the positive x direction. So to the right. So that's the entire acceleration vector. Okay. I'll skip part C because this is just more of the same. You're given some information about the deceleration, enough to find what the acceleration. In this case, it's a deceleration of the piano. Enough to calculate what it is, and then you're given two of the forces and asked for the third person's force. So I'll leave that for you to try on your own, and the solution and check the solution. And then finally, part D, I'll just jump down here. What is the normal force from the floor at any time during this entire scenario? Okay, when the piano's speeding up, slowing down, moving at a constant speed. Well, going back to our equations right here, the normal force only appears in the right-hand equation, which is the vertical equation. And it turns out at all times, it's equal to m times g. 515 kilograms. G, remember, is a positive constant, always. Whenever we want to make a negative, to make a point in the downward direction, we multiply it by -1, right? Like we did up here. But that's to make it that's for a component. When we actually plug in the value, the little g itself, you'll notice that throughout our textbook, throughout all our examples, we're always plugging in positive 9.80. And then this gives us a value of 5,047 newtons. I guess it's three significant figures, so I guess that's going to be 5.05 kilonewtons, or 5.05 times 10 to the 3 newtons. Same thing. Or you could even say 50 newtons. And the assumption would be that this trailing zero here, if there's no period after it, the assumption is that trailing zero is probably not significant, right? It's ambiguous, but it's probably not. Okay. All right, next we're going to go on to example number 4. Okay, and example number 4 is an elevator problem example. Let me zoom out. And there's a classic sort of set of physics problems that ask you um, about standing on a scale in different scenarios, in different situations. And one of the classic ones is when you're inside an elevator, right? Suppose you're standing on a scale inside an elevator and the elevator is moving. Well, as long as everything remains in contact with everything else, then assume that the elevator's vertical motion, right? And by motion, I mean at all times acceleration, velocity, and displacement, right? Whatever those might be of the elevator are the same as you and everything else inside the elevator. So that's going to generally be true when we have things that remain in contact with each other. And that's also true when we're going to have, in the next problem, when we have two boxes that are connected by a taut cord, right? So if this is not a spring, if this cord doesn't stretch, if this is a taut cord, then at all times, the motion of box one and motion of box two and the motion of the system of the boxes are all identical. And by motion, again, I'm using that as a collective term to mean acceleration, velocity, and displacement, all right, of box one, velocity, acceleration of box two, and displacement of box two, velocity, acceleration, displacement of the system of boxes of M total are always exactly the same at all times. So we don't need to put subscripts on those things to distinguish them from each other. Okay, so I don't need to worry about the acceleration of box one is a sub one, the acceleration of box two is a sub two. They're the same. They're the same. And so that's going to be true for the elevator and everything inside the elevator. Okay, so just bear that in mind whenever you see that. So if the elevator is accelerating upward at 2 meters per second, that means you are accelerating upward at 2 meters per second as well. Okay. Now, the other thing to get from this is what a bathroom scale does, or any sort of scale where you rest something on the top of it. So when you put something onto a scale to weigh it, what that scale is actually telling you is not really the true weight of the object. What it's actually telling you is the normal force from the surface below. And the easy way to prove this to yourself is go back to question 3, which I've skipped, and you can see that although the mass of you never changes, if someone else pushes down on you or pulls up on you while you're standing on a scale, what happens? The reading on the scale will change. That's because the normal force from the floor underneath is becoming greater or less as someone pushes down or pulls up on you. Your mass isn't changing, and therefore your weight isn't changing. So your true weight never changes in those cases. The same is true here with this elevator. As the elevator accelerates upward or downward, in order to accelerate you, the floor of the elevator has to push on you either harder or less hard than your weight in order to accomplish that. So the reading on the scale, therefore, that's acting as our sort of like meter, it's acting as our sort of like readout of what the normal force is going to change. So if this is U, we'll call this U, mass M. You have a weight at all times, and that weight is always has a magnitude of mg, regardless of your motion. Right? In order to change that, you'd have to gain or lose mass. And then we have the normal force from the floor, and this does change magnitude. So I'm picking some random length here to draw this normal force vector. But this normal force vector could be greater than the weight, more newtons than the weight, or it could be fewer newtons than the weight, or it could be the same number of newtons as the weight, depending on the acceleration of you and the elevator and everything inside. Okay. So just for, so this diagram can't be 100% accurate if I just draw it once. I'd have to draw it multiple times for all the scenarios here. But this is just a little inventory here to give us our rough list of all of the forces and rough directions. Okay, so I'm going to choose my axes. And in this case, again, there are no x components of any forces. There's no motion in the horizontal direction. So it's actually surplus for me to define an x direction. It's unnecessary. You could leave it undefined if you wanted to. Okay, we're not going to use it. Now we can decompose all of these into components. And really all we're going to care about now is whether the y components are positive or negative, right? So again, we're going to do it all by inspection. No need to do any trigonometry here. So normal force, it has no x component, and the y component is the entire magnitude in the positive y direction. Weight has no x component. I'll zoom back in. And the magnitude, the entire magnitude is in the negative y direction. And that's it. Okay. So that's all of our forces. Now we can apply Newton's second law. And we'll end up getting an expression here, okay, for adding up the y components of all these forces. That's it. Okay, that relates the acceleration of u, mass m, right? So this is u. The acceleration of u to the normal force from the floor. And everything else is constant. Your mass is constant and the value of little g is constant. Okay. So as long as this free body diagram doesn't change, we don't add any forces or delete any of these forces or change the direction of any of them, right? As long as the free body diagram remains and these decompositions of the forces, as long as this all remains static, it doesn't matter if they get stronger or weaker, right? I'm talking about directions or just the presence of new forces. Then this equation will hold. So in other words, the acceleration can have any value, the normal force can have any value, and this free body diagram and this equation are still true. All right, so this is what the scale reading will be. The scale will read the magnitude of the normal force, right? And of course, we know the direction is always upward, right, coming out of the floor. All right, so now we can answer all these questions here. It might be nice to just go ahead and calculate our weight because it looks like our weight will appear over and over again as m times g. So it'd be nice to just sort of calculate this, okay, and have it handy. So I'll ask my calculator what's 50 times 9.8. My calculator tells me it's 490 newtons. Okay, so that's the magnitude of the weight. All right, good. So now that'll just save me one more math step later. Suppose now the elevator is accelerating upward. So we have upward and we have the magnitude here. So what that means is the y component of the acceleration is going to be positive 2 meters per second squared. Of course, the x component is always 0. So what's the reading going to be on the scale now? All right, well, first of all, let's sort of guesstimate. Let's just make a sort of prediction. We know that your true weight is 490 newtons. In theory, if the elevator is completely at rest and you stand on the scale, then we would expect the scale to read 490, right? Because then what we'd have is we'd have a static equilibrium, right? Your acceleration would be 0. If the elevator were at rest and you were at rest, the acceleration would be 0, and normal force would just be equal to mg. Now, what if the elevator is accelerating upward? Well, in order to do that, the floor has to push upward on you harder than your weight. It has to completely counteract your weight, and in addition to that, provide more newtons of force in the upward direction to accelerate you upward, right? So that way the net force on you will be in the upward direction. And when the net force on you is in the upward direction, your acceleration can be in the upward direction. So we can already eliminate answer choices A, B, and C because we already know that the normal force from the scale needs to be greater than your weight. Now we can actually calculate what it is and find out. Let's use this equation here. Normal force minus 490 newtons. So here's the extra force that the floor must provide to accelerate you upward, right? These are all 3 sig figs, I think. So that means that the reading from the scale, I'm just going to squeeze in one more line of writing here, is equal to 590 newtons. Okay. I'm going to skip scenario 2 and let you try that one. Okay. And then scenario 3, suppose that the reading on the scale, actually, you know what? I will skip this as well. Okay. But I'll just point out one more thing. And I'll say, suppose that you have a positive acceleration like we do in scenario 1. So this is just talking about the thought question here. Suppose that you have a positive acceleration. Is the elevator speeding up or is it slowing down? Okay, so we have an upward acceleration. Is the elevator speeding up or slowing down? Or can either one be true? Well, you might remember from back in our one-dimensional kinematics, when you have a car that has it's possible for a car traveling along the x-axis to have a positive velocity and a positive acceleration, positive velocity and negative acceleration, negative velocity and positive acceleration, and negative velocity and negative acceleration. And 2 of those are cases where the car is speeding up, and 2 of those are cases where the car is slowing down, right? So if the elevator has an upward acceleration, it would depend on whether it could be either speeding up or slowing down, depending on whether it was moving upward or moving downward at the time. So if it is moving upward, meaning it has an upward velocity, and we also give it an upward acceleration at the same time, that means it's speeding up, right? So if it has some positive velocity, like 1 meter per second, and then we also accelerate it at positive 2 meters per second every second, then that means its velocity is going to be +1, +3, +5, +7, and it's speeding up. On the other hand, what if the elevator were descending? What if it were moving downward? So it had an acceleration of like -5 meters per second, and we give it a positive acceleration. So if its velocity were -5 meters per second and a positive acceleration, that means the velocity is going to go -5, -3, -1. That's slowing down. So this could be an ascending elevator that's speeding up, or this could be a descending elevator that's slowing down. Either one could be the case here. Okay. Finally, the one last thing that we'll check in on is, what if the elevator is in free fall? What's the acceleration in that case of you and the elevator? Well, what the definition of free fall is when the only force acting on you is your weight, right? So the only force acting on you and the elevator and everything inside of it would just be the weight only. So, and that would be like if the cable snaps and the elevator starts and there's no air resistance and the elevator starts to plummet downward. Okay. So in that case, what happens? Well, then the only force acting on you is going to be your weight. Therefore, your acceleration, there will be no normal force at all. And the acceleration will be equal to -g, because we have 0 plus your weight plus your, pardon me, 0 plus minus your weight is equal to m times your acceleration. So therefore, your acceleration is -g y component. X component is 0. So this is just like a projectile, right? Projectiles are in free fall. They have 0 x component of acceleration, and y component of acceleration is always -g if we choose the positive y direction to be upward. Here, I'll zoom out. Okay. And in this particular case, therefore, we get that the normal force minus mg is equal to m times -g. So that means that the normal force from the floor is 0, and the reading on the scale will be 0, right? Because you and the scale and the elevator floor are all accelerating toward the Earth with the exact same acceleration, and you're all falling away from each other at the same rate. So there's no way for the floor to push back on you. So this is false. The reading on the scale will be 0, not your weight. Your weight is still 490 newtons. All right, great. Let's finally, I'm going to pause the lecture here and just to make the file size a little smaller. And when we resume, I'll pick up with problem 6 on tutorial 13A, and then I'll just have 2 more examples after that from 13B, problems 1 and 3.